In this video, we're going to take a look at the sine and cosine functions again, but now we're going to look at the graphs of those functions. And then we're also going to work on applying transformations to these functions as well. So first, though, we're just going to try to get an idea of what the cosine function and the sine function actually look like. And so first of all, when I talk about graphing them, let's understand that what is the input for the cosine and what is the input for the sine? Well, we're inputting an angle, right? The angle on a circle. And what is it output? Well, the cosine outputs the ratio of the x value to the radius of that circle, and the sine outputs the ratio of the y value to the radius. But again, I think for our purposes here, let's just in our minds think about the unit circle, right? Because if we're talking about the unit circle, then the cosine is the x value on the unit circle and the sine is the y value on the unit circle. And so that's what I have over here in this table, is just that idea that on the unit circle, the cosine and sine give us the x and y values. So over here on the graph, I've put theta on the x-axis, right, where we put the input, and then the cosine of theta is on the y-axis. Okay, so let's start with cosine. So I've over here on the table, I've put some values that are in quadrant 1 that we should have memorized about both sine and cosine, and then I've put a couple others: pi, 3 pi over 2, and 2 pi. So let's start with just 0. When theta equals 0, the cosine is equal to 1. When it's pi over 2, you can see that cosine is 0. When it is 3 pi over 2, cosine is -1. Or sorry, when it's pi, it's -1. When it's 3 pi over 2, it's back to 0. And then when it's back at 2 pi, I'm back up at 1. So I got a picture here, but then the question becomes, okay, so what happens between these points? Is it just kind of a V? Do I just make a giant V here, like an absolute value graph? So we need to know what's going on in between. So I think what we might find helpful is let's make note of what some of these values are that are in quadrant 1. Well, I know 1/2 is 0.5, of course. That's pretty straightforward. Square root of 2 over 2, that is about 0.707. And then square root of 3 over 2 is 0.866 approximately. So that gives us an idea of where exactly the y values ought to be, what exactly the cosine values ought to be at these theta values. So let's try to mark these on our graph. So first of all, pi over 4, right, is exactly half of pi over 2, so that puts pi over 4 right there. And then understand that pi over 2 is the same thing as 3 pi over 6. So if I just split this into thirds, from 0 to pi over 2 into thirds, then that would have to be 1 pi over 6. This would have to be 2 pi over 6, which simplifies to pi over 3. And then, of course, the first one I drew there in the middle was pi over 4. So now what I can do is I can ballpark where 0.866 is. That's up here pretty high, right? Pretty close to 1, so I'll put a dot right there. Oops, or there's that weird vertical line again. Let me erase that. All right, so we're right about here. And then 0.707 is just a little lower, not much. And then 1/2, we could say, is probably about right here. So we can graph these, and so we can see it's not this straight line. It's kind of this arcing situation. And so that kind of gives us an idea of what this behavior is. So this is really, and that's not perfect, but that's kind of what our function looks like. And so the cosine value to the right of 0, the cosine function, looks like this. But what's happening to the left? Well, it turns out, and doesn't take long to check, that it's completely symmetric, right? If you go clockwise around the unit circle, you would find that the cosine value matches with the ones I just plotted. And so here's our cosine function graphed here. And you'll just have to forgive me throughout this section. It's kind of tough to graph on using this computer pen. But you get the picture here. So this is basically the behavior of cosine. Then we can do the same thing for sine. So at theta equals 0, where the sine is 0. At pi over 2, it's 1. At pi is 0. 3 pi over 2, it's -1. At 2 pi, it's back to 0. And so here's what we have going for sine. Okay. And then over here, if we plot values on the unit circle going counterclockwise, we would find that these are the values that we're interested in. Okay. And so this is basically what sine looks like. So before we move on from this, just a couple of things we should take note of. First of all, you can put any angles you want into the cosine and sine. You could put 1,578 degrees, really huge number, and you're going to be able to find the cosine value for it and the sine value for it, right? Because you can just keep going around the circle. So the domain is all real numbers, right, or -infinity to infinity. The range, however, sine and cosine never get outside of the -1 to 1 range. So that's the range of our function. And then the other thing I want you to notice is this business of symmetry. Okay, so symmetry is something that you probably studied at one point in a previous pre-calculus class. And that is, if I plug in a negative value for my input, what does that do to the y value? Okay, so in other words, if I go here to, let's start with cosine. If I go here to a particular angle, which I'm going to call negative theta, how does that compare to that same angle over here, positive theta? Well, it's pretty clear that it's the same on both sides, right? It doesn't matter where I go, it'll be the same. So if I go way back here versus about the same distance over here, the y value is the same. So we would say that the cosine function has even symmetry, meaning that if you plug in the negative theta, that's the same as if you would have just plugged in positive theta. Sine doesn't have that exact same property, but it has a property nonetheless. So if right here is negative theta, I go down to this particular y value, and then if I go up about the same distance here, so this is positive theta, what you'll notice is that the distance from the x-axis is the same, it's just the opposite. So if you plug in the sine of negative theta, you just get the opposite of the sine of theta. And then the last thing I want to point out here is that both of these functions repeat themselves after 2 pi. So we call this the period of the function. So functions that repeat themselves, we say they have a period that is equal to however long it takes in terms of the x-axis for it to repeat itself. And you can see both of these start repeating themselves after 2 pi. Okay, so we want to start talking about transformations of these trigonometric functions now that we have an idea of how they're graphed. So let's start with f of x equals the sine of x minus 2. So we remember that subtracting 2 shifts our function down 2. Now, so we could think of this as a vertical shift down 2. So I could graph the sine function here, and then just take all the y values and move them down 2, and then have my function. But another way of looking at this is that on the previous page, let me just flip back there real quick. On the previous page, both of these functions are oscillating about the line y equals 0. Okay, so in other words, y equals 0 is their midline that they're oscillating above and below. So you kind of think of this like as an ocean wave, if it helps you, and think of, okay, here is exact sea level is the x-axis, but then the waves, of course, are going up and down. Okay, so that's the midline. So another way of thinking of this is that taking -2 here really just moves the midline down. And so what you might find helpful is just to kind of, real lightly, don't make this real obvious, but just real lightly kind of put a dashed line down at -2, indicating that, okay, now the sine function is just going to oscillate about that. That's really what's going to happen. And if you do that, then you can kind of think of y equals -2 as your kind of new midline, or new equilibrium is another word for it. And then you can just work on graphing the sine function as we did on the previous page. So what do I know about sine? At x equals 0, it's right at the midline. And then it starts by going up 1, and then when I get to pi, I'm back at 0. When I get to 3 pi over 2, I'm back at -1, and then back at 0. And then on the other side, we have that odd symmetry where all the y values are just flipped from what they were on the right side. All right, so I can, ooh, that's ugly. There we go. That's still ugly, but acceptable, I guess. So now I've got this function here. Okay. And yeah, this is not a great looking graph that I've created here, but it's getting the point across. So just move it down 2, and then you can sketch your sine function from there. So anytime you see y equals sine of x plus k, or y equals cosine of x plus k, y equals k is going to be your midline. In this example, we're going to look at another couple of types of transformations. First of all, this negative here we should recognize as a vertical flip or vertical reflection. It's just going to take all of our y values and make them the opposite of what they were. And then the 3 here is a vertical, in this case a stretch, multiplying all the y values by 3. So let's understand, first of all, that really there's a name that we want to give to this idea of a vertical stretch or shrink, and that is the amplitude. And so we'll tend to refer to that as the amplitude basically from here on out when it comes to a sine function or a cosine function. But notice that what we would say here is that our amplitude is 3. It's not -3. So the amplitude is just the absolute value. So it doesn't matter if there's a negative in front or not. You wouldn't say the amplitude is negative. The amplitude is just the absolute value of whatever coefficient's there. Now, since we have 2 things to do here, 2 things to apply, and we're just now learning what the cosine function looks like, I think it might not be a terrible idea just to make a quick sketch of the original cosine function. So that we can reference it as we're doing these problems. And so what you can do is, even on assessments or homework or whatever, feel free to just kind of sketch the original as you are trying to, just kind of get used to applying these transformations. So that's not something you have to do, but you might find it helpful. Okay, so there's my original, or at least a good enough representation of it. So let's think about what is it that this is going to do. It's going to flip y values, but then it's also going to multiply them by 3. So this y value here that was at 1 must now be down at -3. This y value that was at 0, well, nothing should happen to that, right? Because you flip 0, it's still 0, and when you multiply it by 3, it's still 0. This one that was at -1, though, now should be at +3. This should be back at 0, and then this one should be back down at -3. And so you kind of get the picture here. And once you really, in your mind, have it down solid what the cosine function, just y equals cosine of x, looks like, then it's probably unnecessary for you to draw it to begin with. But as we're beginning here, that's kind of nice. And so of course I see I still have this oscillating function, this by the way, we call these sinusoidal functions, and so it doesn't matter if I'm talking about sine or cosine. Both of them we refer to as sinusoidal functions. So we still have this sinusoidal behavior. But obviously the amplitude is much bigger, and and we've also flipped it. Okay. In this example, we're going to graph f of x equals the sine of 2x. And so let's start this example like we did the last one. Let's go ahead and give a quick sketch of y equals the sine of x without any transformations on it. So we know it looks something like this. Okay. I'm just gonna do that one little part. I think that'll be sufficient to give us an idea of what's going on. So I'm going to change colors here and then set to work on sketching the graph of the sine of 2x. So what is this 2 doing? Well, remember that is a horizontal shrink, right? It's a shrink because we think of things happening now twice as often as they would have, or twice as soon as they would have. So a horizontal shrink by a factor of 2. So a way that I could think of this is, all right, I'm going to start at 0, and the same thing's going to be happening at 0 as before. So in other words, before x equaled 0 when y was 0, and that's not going to change by multiplying the x value by 2. However, now I'm going to get y equals 1 to happen twice as fast as it did before. So if I make a little notch here, that should put that y value back to or back here to half of this point, and this is obviously pi over 2. So now it's at pi over 4. And before we got back to 0 at pi, now we're going to get back to 0 at pi over 2. And so now you can kind of play this game with all these points. This was happening at 3 pi over 2. Now it's going to happen at 3 pi over 4. So that's right here. And then we completed our cycle after 2 pi. So now instead we're going to complete our cycle after pi. So this gives us one complete cycle of sine. But the nice thing is, once I graph it once, graph one cycle of it, then I can just follow the pattern for the rest of it. So after another pi, this thing repeats itself, and so I don't have to work too hard from here. I just kind of copy myself from here. Oops. Okay. That one didn't quite make it down low enough. Sorry about that. And then I can go to the other side. Now I know that sine is an odd function, so whatever was happening on the right side here, the same thing's happening on the left but negative. So I can just kind of use that symmetry to get the picture over here. And so here's another cycle going back in this direction. And then one more cycle here. So we can see that 2x in the argument of our function really changed how often it was that things are happening. Let's look at one more here. We've got the g of x equals 3 times the cosine of 1/2 x. And once again, let me go ahead and just give a quick sketch of our cosine function without any transformations applied. And yeah, I'm just going to go ahead and do that. Okay, just do one period of it like I did in the previous problem. All right, so so what are those transformations? Well, I have a 3 that is changing my amplitude to 3, but then I have this 1/2, right? So what does that mean? Things are happening half as often, I suppose. So this is a horizontal stretch. Things are happening half as often. So so what I can do here is say, all right, well, the 3 is going to take my y value and multiply it by 3. Okay, so now that puts me up here, but I'm still at 0, so I've got that same starting point. However, now when I get back to 0 here, that was happening at pi over 2, right? That was pi over 2. So now it's happening, it's happening half as fast as it would have. So now I go over and I put it right here at pi. All right, and then this point was happening at pi. Now it should happen half as fast, so that should put me all the way over here at 2 pi. But again, the 3 triples that y value, so instead of -1, it should be at -3. And so I still have the same sort of behavior, but I kind of have to stop here. So this is what I can see is that my my cosine function, I'm not even going to see a full period. It's just going to, I'm just going to see half of it. Okay, but that's okay because I know that on the other side the same thing happens, right? So normally this would have gone down to 0 at pi over 2. At pi over 2. Now it's going to wait to go down to 0 until negative pi. Excuse me, I meant to say negative pi over 2 here. And then typically I would have been down at -1 at negative pi, but now I'm going to be down there at -2 pi, and then I'm again going to triple it, and that's going to be -3. And so then I can show a complete cycle between the negative side and the positive side. Okay, so this business of a horizontal stretch, it's always kind of the hardest transformation to apply. So I want to give us a different way of thinking about this. So down here at the bottom, it says y is equal to the sine of b times x, and y equals the cosine of b times x. Those indicate some sort of a horizontal stretch or shrink. Okay, but what I think is really effective is to think about what does this number here do to the period. So another way of thinking through applying this transformation would be to say this. Let's just take this formula here that they gave us. When I see this 1/2, I'm going to take 2 pi divided by that number b, which is 1/2, and that should be my period. Well, that would give me 2 pi times the reciprocal, 2 over 1, which is 4 pi. So the other way I could have thought of this was I could have said to myself, you know what, I'm just going to graph cosine. But I know that the period of this cosine function that I'm graphing is 4 pi instead of 2 pi. So that means I don't complete a cycle until I get all the way out to 4 pi, which would be out here, right? And so then I could complete the whole cycle all on the positive side. But it's also fair to then say, well, I'm going to go, say, from 0 to 2 pi, and then I'm going to have the other half of that from negative 2 pi to 0 so that I know I'm going from, or I have a period of 4 pi. Okay, let me just backtrack to that last example. Let's see how that works here. So I would say my period is 2 pi divided by 2, which of course is pi. So I could look at this and just say, all right, I'm going to graph the sine function, but I'm just going to make sure I get done with a full period after pi. Okay, so then I make sure that that happens. And so you can see why it's so important to understand the behavior of the basic cosine function and the basic sine function, because you have to have that in your memory banks in order to be able to quickly say, oh, here's my new period, so this is how I'm going to sketch the graph. In all the problems that we've done so far, we've had the notches on the axes of our graph already done for us. Okay, and so here's one where it's just kind of left blank because we're not assuming too much about exactly what this thing's going to look like. So so let's just kind of take this one at a time and identify these different transformations. So first of all, we do have a flip, and I guess I should be specific, a vertical flip. A vertical flip. This 3 tells me that my amplitude is equal to 3. And then remember, when I add 2 outside of the argument of my function, this is my midline. So the midline, or the equilibrium, is y equals 2. And then the only other part is this this pi over 2. And so remember, that is giving me information about my period. So what I can say, remember, is the period is equal to 2 pi divided by pi over 2. So that's 2 pi times the reciprocal of pi over 2. And so what we get there is we have those pi's canceling. And so now my period is not any kind of multiple of pi over 2 or a fraction of pi over 2, but it's just the number 4. So because of that, you can see why I left this blank, because I don't want to put tick marks at fractions or multiples of pi. I just don't want to do that, because it's this thing has a period that doesn't involve pi at all. So what I want to do is say, okay, I know this thing's going to get through one period in 4, so how about I just go ahead and label this 1, 2, 3, 4. So then I'm putting the notches in and deciding how I'm going to show one period being completed. And I guess I should probably do that on the other side as well. This is negative 4. All right, and now as far as the y value tick marks, I can see my amplitude is 3. So my amplitude is 3, but also my midline is 2. So if I go up to my midline here, I know I'm going to need to be able to go 3 below and 3 above that midline. Okay, so need to leave enough room that I'm able to do that to get up to 5, and then I need to also get down to negative 1. And so with all of that information, I'm actually ready to go. The only thing that I need to think about is I do have this vertical flip. So typically, cosine starts at its maximum value above the midline, right? And that's where it gets going. So because I flipped it, that means it should be at its minimum value, so that would be down 3 from the midline. And then I know that once one period is completed, cosine should be right back where it started. And exactly halfway through a period, it should be just on the other side of the midline. And then a quarter of the way, I should be at 0, but in this case my 0 is just where my midline is, and so I should be right back there, and also 3/4 of the way I should be right there. Okay, so you can see how I can use all this information that we've learned, and I actually didn't really have to think about transformations all that much. Okay, and I can go over here, do the same. So when I'm at -4, I should be down here with another period completed. Exactly halfway through, I should be up at the maximum, and then in between those, I should be at the midline again. And so that allows me to get a nice sketch of this cosine function. Ooh, there we go. Okay, end of that wasn't so good. Ignore that little vertical line there. So I do want to do an example where we show one more type of a transformation. So this is what we would call a horizontal shift. And it would be a horizontal shift, remember, to the left. And the reason it's to the left, remember, is you think of this as things are happening 3 pi over 4 units sooner. So that's why we shift to the left. It's kind of the opposite of, I guess, what you might expect of it. And in terms of this class, we really refer to these types of things as phase shifts. So how do we apply this? Well, first let's just give a sketch of one period of y equals the sine of x. So there we go. All right, and so we know that it we know those notches are in pi over 2 pi, 3 pi over 2, and 2 pi. But looks like multiples of pi over 4 are going to be important to us. So let's go ahead and make one more notch in between each one, noting that these red notches are at multiples of pi over 4. All right, so if I am shifting to the left 3 pi over 4, then this starting point here should be right here instead, right at 3 pi over 4. Okay, and then this ending point should be back 3 pi over 4 as well, so back 1, 2, 3 pi over 4. And then this 0 right here should be back 1, 2, 3 pi over 4. Same thing with this this value of 1 here, 1, 2, 3 pi over 4, and then same thing here, 1, 2, 3 pi over 4. And so we can pretty quickly, I guess, get a sketch of this sine function shifted back 3 pi over 4. So when we are doing this, we haven't really changed the shape, right? We haven't changed the period. So it retains the same shape, but just things happen sooner, that's all. And I could keep graphing it, but I'll be lazy and just graph that one period. So now that we've introduced all the different types of transformations that we could be doing to our sine and cosine functions, now we can kind of summarize it all, which is nice. So generally, we are going to have functions that look like this. And, some of these transformations may not be present necessarily in every problem, but now we have the ability to deal with all of them at once. The one thing that I need to emphasize here is that in order to be able to know what the true phase shift is for a function, you must have it in this form where the b value is factored out and you have x minus h. So for example, because this 1/2 is factored out of these parentheses, I can start by saying that we say 2 pi is the shift left, right? I guess to be more proper, it's the phase shift. We'll see examples later where it is not given to us in this form, and we need to understand that in order to see that true phase shift, you would want to have it in this factored form. Okay, but this one already is. So we have a shift left of 2 pi. First of all, we can see that 2 is the amplitude. We can see that the midline is y equals -1. And we can also see that the period, okay, the period is equal to 2 pi over b, which is 1/2. So that's 2 pi times the reciprocal, which is 2 over 1, so 4 pi. So it's going to take me 4 pi to get through one cycle. I'm going to oscillate up and down about the line y equals -1. The amplitude is 2, and then I'm going to shift this whole thing left 2 pi. So with all this information, I can start to get an idea of where I should put my notches. So I'm kind of thinking maybe -1 right here. Because the amplitude is 2, I need to leave enough space where I can get down to fairly easily. Then I go up, then I go up 2 from that midline. So it's probably a decent idea just to kind of put a little dotted line there to represent the midline. Try to keep it a little straighter than I'm able to. All right, and then we'll think about, okay, well, what about the x-axis? How should I be labeling that? Well, if I'm going to go through one full period in 4 pi, I think it makes a lot of sense to go ahead and count by pi and be able to fit 4 pi in there so that I get one cycle in that amount of space. It's generally nice to be able to show about 2 cycles whenever you're making a graph. Okay. So this is 4 pi here and -4 pi here. All right, so then from there, to get this thing started, let's take into account the phase shift. So I have the function sine, and I know sine at x equals 0 would typically start at y equals 0, or at the midline, I should say. But since I'm shifting to the left 2 pi, I'm going to have kind of the starting point be right here. And I know that a full cycle has to be completed after 4 pi. So this is -2 pi, so plus a pi, plus a pi, plus a pi, plus 4 pi puts me right there. So one full cycle needs to be completed. Halfway through a full cycle, I know that sine is back at 0. And then halfway between those 2 points, it should be up at its maximum. And halfway between these 2 points, it should be down at its minimum. And so we can get one full cycle pretty easily sketched. Just like that. Okay. And I'm going to go ahead and I think it's nice to go a little bit further. So here's, I'm going to go to 4 pi, halfway between there. So I'll show a half of a period on this side. And I can do the same thing over here, another half of a period on this side. All right. So one last example here. Here I've got f of x equals the cosine of 2x minus pi over 2. So here's what I'm talking about, where notice how this is not in this proper form here. I do not have it as b times the quantity x minus h. So we kind of have two options for dealing with this. One is to go ahead and factor out what's inside the argument there. So what I could do is say that f of x could be rewritten as the cosine of, and I can pull the 2 out, and then just ask myself, okay, If I pull 2 out, what has to be here in the first term? Well, just x, right? But what would have to be there in the second term? So remember, I need 2 times this number to equal pi over 2. Well, if I'm multiplying something by 2 to make pi over 2, that thing probably needs to be pi over 4. And you can test to make sure. If I take 2 times pi over 4, in fact, I do get pi over 2. So here's what this tells me. This tells me that I have a phase shift and since it's minus, it's to the right, pi over 4. And I couldn't see that over here, but now I can. So I have a phase shift to the right, pi over 4. And then, of course, the 2 is telling me that my period is 2 pi over 2, which is equal to pi. All right, so I know my period. I know that I'm shifting pi over 4. My amplitude is 1. And I don't have a change in midline, right? So maybe just to be careful here, I'll just mention amplitude is equal to 1, and then the midline is just y equals 0. So because my period is pi, I think it makes a lot of sense to go ahead and go all the way out here to pi and back here to negative pi. I think that makes sense. And so since we're shifting by pi over 4, I also think it makes sense to break this up as multiples of pi over 4. Okay, so you can see this is pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and pi. All right, so we really do have all the information we need. I'm going to go ahead and mark that as 1 and mark that as negative 1. And so because of the fact that I have this phase shift of pi over 4, I know that cosine normally would be starting at its maximum at 0, but instead it's going to be starting there at pi over 4. And then it's going to have to get itself through one full cycle after pi. So adding pi over 4 plus pi is going to be 5 pi over 4. So a little bit off here, at 5 pi over 4 is where it should be back at its maximum again. And exactly halfway between there, it should be down at its minimum. And then it should be at these zeros. Then I can go to the other side and do the same thing. So if I backtrack by pi, or by 4 pi over 4, 1, 2, 3, 4, that puts me at negative 3 pi over 4. I should be back at the maximum, halfway between, down at the minimum, and then at 0 and at 0. Now, as soon as I'm done sketching this, I want to show one other way of thinking through this phase shift business, just in case you want an alternate way besides this factoring. So the other way to do it is this: you can say to yourself that the starting point for cosine is typically x equals 0. So to figure out where the new starting point would just be when the thing inside of the cosine is equal to 0, right? So what you could do is just take 2x minus pi over 2 and set it equal to 0. Add pi over 2 to both sides. Let me change colors here so I don't run into my graph and make it messy. But I could add pi over 2 to both sides. and I really didn't plan well in terms of where to do this work, so let me go down below. And so that gives me 2x equals pi over 2. But then, of course, to get x completely by itself, I can just multiply both sides of this by a half. Get those to cancel, and so I get x is equal to pi over 4. So the way to interpret this is the following. Instead of factoring out and saying, I realize that this is a shift to the right pi over 4, I could say, I know that my normal starting point is at 0. So when the argument for the cosine is 0, that becomes the new starting point. So I say 2x minus pi over 2 equals 0. Solve for x. My new starting point is x equals pi over 4. And so this is just an alternate way of doing it. It doesn't matter to me which way you think about it. So you just kind of pick whichever of these two methods works best for you. And it's worth noting that you could do the same. You could have done the same thing here. I could have done that business of new starting point, even though it was already factored. I could say 1/2 times x plus 2 pi should equal 0. Okay, but of course if you multiply both sides by 2, you still have 0. And then you can see if you subtract 2 pi from both sides, you get negative 2 pi. So our new starting point is at negative 2 pi, and that's exactly where the new starting point for sine was.